Hi, I'm Professor Seth Chandler from the University of Houston Law Center. This video is on using neural networks for prediction. It's part of the course Analytic Methods for Lawyers, but it really can be used by anyone involved in neural networks. If you haven't watched the introductory essay and video that goes through neural networks, I would suggest that you do so because this is really going to be building on what we learned there and assume that you understood it. In this essay and video, I want you to understand the arts of architecture and training. And I say art because there's no general theory yet on how to either design or train neural networks. It's partly a matter of understanding what's going on inside and really partly a matter of experience. What I want to do in this essay is discuss the balance between getting a strong fit on the training data and having the model generalize well to new data. We're going to discuss 4 techniques to prevent overfitting: validation sets, dropout, regularization, and architectural design. I also want to show you 2 other techniques. One is how to predict multiple values simultaneously, and also how to design a custom loss function instead of the pre-built loss layers. And what this latter technique will do is it'll really let you train your network to do anything that you want. Let's discuss using networks for prediction. And first, let's get the data. We're going to be using the Boston housing data. I'm sorry if it's a little tedious, but it's really good data for pedagogical purposes. All right, we've snarfed it in. And now let's look at some architecture. I'm going to build a network that's similar to the one that I used in the introductory essay, but it's going to be a little bit deeper. That is, it's going to have more layers than the one I built previously. And I'm going to introduce a more advanced nonlinearity. In the introductory lecture, we used a ramp. Here, I want to use something called a parametric ramp layer. A ramp, it doesn't have any trainable parameters. There's nothing to be learned. If the input is less than or equal to 0, the output is 0. And if the input is greater than 0, then the output is the same as the input. With a parametric ramp layer, however, every negative value no longer has a value of 0. In fact, none of them do. Rather, for each of the input slots, there's an associated slope parameter, so that if the input has 2 items, it's a length 2 vector, there are 2 slope parameters. And here's what you do. Supposing one of the inputs coming into the network is -3. You multiply that -3 by the slope parameter associated with that node, say it's 0.5, and therefore -3 translates to -1.5. Another input going into the same layer might have a slope parameter of 0.2, and so if a -10 came in, the result would be a -2. For positive values, it works exactly the same as a ramp. It just returns the input. So let's look at some Wolfram language code for declaring a parametric ramp layer. Here it is. And you can see that it has a slope of, the first input's going to have a slope of 0.2, the second input's going to have a slope of 0.5, and it's going to take 2 values. And so that's our ramp layer, and now I'm just going to apply our ramp layer to the value 1, -6, -2, 3, and we'll see what it returns. And let's try and do it by hand. The 1 is positive, so it should return a 1. The -6 is negative, so it should return 0.5 because it's the second value multiplied by -6, which is -3. Looking at this one, we have -2. Oh, that's negative, but it's in the first position, so we multiply by 0.2 to get 0.4. The 3 is positive, and we leave it alone. And so let's see if, well, I cheated, I guess. In fact, let's clean out our kernel here, and I'll be right back. All right, I cleaned out the kernel, and let's run this code. All right, and we get exactly what I predicted. So oftentimes when you actually construct a neural network, you don't set the slope yourself. It's one of the things that's initialized, and in general, slopes are set to 0.1. What's going to happen during training, though, is that the network is going to learn the value of these slope vectors that minimizes whatever your loss function is. So now we can build the neural network. I'm going to use 3 linear layers. One has 50 nodes, the second has 30 nodes, and the final one is that compressor that's going to boil everything down to one number. So here's what our nodes look like. We're going to have 13 values coming in because that's how many features there are in the Boston data set. We'll have our first parametric ramp layer. How many values are coming in? Well, it's the same as the number of nodes coming out of the first linear layer. Here's our second linear layer. How many nodes does it have? Well, it has 30, but how many are coming in? It has 50 coming in from the preceding linear layer, and parametric ramp layers don't change the number of nodes. Then we've got our second parametric ramp layer riffled in, and it also has the same number of nodes coming in as the second linear layer had going out. Finally, we have our compressor, which has the same number of nodes coming in as the preceding layer had coming out, and it's going to output one value. And finally, we have our mean squared loss layer to figure out what our loss is. So those are our nodes. Here are our edges, and we do it the same way I did it in the rigorous way that I showed in the introductory video. We're going to start with our non-layer ports features. That's going to go to the input of linear 1. Coming out of linear 1 goes to the input of ramp 1. The output of ramp 1 goes to the input of linear 2. The output of linear 2 goes to the input of ramp 2. The output of ramp 2 goes to the input of the compressor. The output of the compressor goes 2 places. It goes to the mean squared error input port, and it also goes to a non-layer port predictions that we can observe. Finally, what else does the mean squared error layer need? It needs to know what the targets were, and so we connect the non-layer port targets to the target input port of the mean squared error layer. All right, now we're ready to build our network. Remember how NetGraph works. NetGraph, the first argument is the definition of the nodes. The second argument is the connectivity structure. And then we're going to have information on the non-layer ports. The features are a length 13 vector. The targets are a scalar, and I want the predictions to be a scalar. And remember, information with full summary graphic produces a nice picture of the network. And because our network is not initialized, let me get rid of these outputs. They should have been gotten rid of before. And a little error message we'll see in a moment. Let's go back. Here we go. I think I was saying that information with full summary graphic produces a picture of the network. And it's pink because it hasn't been initialized yet. All right, we're ready for training. So our command is nettrain. Our architecture is BostonNet that we just built. We're going to be using the Boston training data, which I see is not defined because it's blue. We want everything back, everything that it can tell us, and I want to run this thing for 30 seconds. And I just figured out why Boston training data is blue. Remember when I killed the kernel? I also apparently forgot to reevaluate the data. All right, so now the data is sucked in, and now our Boston training data is a delightful black. And so let's start training away. All right, and you can see that the loss is decreasing as we move forwards. You can see that it's using something called the atom optimizer, which we'll talk about in the next video, I believe, or possibly 2 after that. And it's just marching through, keeping a constant learning rate here. Doesn't look like that's changing. We'll talk about that as well in a later video. And at the end of the day, our 30 seconds are up, and we have a net train results object. To get the train network out of the trained results object, I hope you remember that you simply use the trained net property. We're going to call the train network Boston TN for trained network, and we'll get a picture of it. Picture really won't be much different because we don't change the architecture during training. We simply change the learnable parameters. Here, learnable parameters are in the linear layer and in the parametric ramp layers where it's learning the slope. Okay? The output, we have two things coming out, and that clues us in that the form of the output will be an association where the keys are the names of the output ports. One thing we could do would be to just see how our trained network performs on the first two homes in the Boston training data set. And those we've seen before, these homes seem to be valued in about that range. It's calculating what the loss is on each of those homes. Doesn't look like our second home did so well. But in any event, what we can do is by using our network over all of our test data, extracting the prediction key, we can then compare the actual predictions, which we'll have calculated there, with the true values of the home, use predictor measurements as we learned in the introductory machine learning materials to get a predictor measurements object, which is going to give us a clue how we performed. And that should be predictions. And so it did okay. R squared of 0.676, not the best thing I've ever seen, but that's what we got. You know, when you don't get a great result on your neural network, one possibility, not the only one, but one possibility is that you're overfitting. And while you've done really nicely on the training data, it's just not going to generalize well when it goes to data it's never seen before. So what I want to do now is discuss 4 methods to be used with neural networks to prevent overfitting, or at least to reduce it. And those 4 methods are validation sets, dropout, regularization, and architectural design. Let's start with validation sets. We've seen validation sets before, and we can use them here as well. The syntax is basically this. It's an option to net train, and by saying scaled 0.2, what that means is you want 20% of the training data to be set aside for validation. And so what we can now do is watch the R squared value as it trains, and to stop the training if on the validation set there hasn't been an improvement of 0.001 in the R squared for 100 rounds. The idea here is that you don't want to keep training and training and training and reducing the loss on the training data per se, unless you're also making progress on the validation set. Because if you're making progress on the training data but not making progress on the validation set, that's a sign that you're simply overfitting. So let's watch this in action. And remember, the orange line is the training data, the blue line is the validation set. They're pretty close to each other here. They're kind of converging. And now, do you see what happened? The the training set continued to make progress, but our validation set wasn't doing any better. And so the training terminated. Let's see how we actually perform now. And our R squared is significantly better. And so I need to actually change this. I'm not sure what happened before. All right, then when I just let the thing run for 30 seconds, we can eliminate that. All right, so good. Use of a validation set was actually quite helpful here, along with a stopping criteria that said if you don't have improvement in the validation set for 100 rounds, I want you to stop. One other thing you might notice in trainings, as here actually, for a lot of this period, the blue line, the validation set, is below the orange line, and you might ask, how could that be? And basically, it's luck. It may just be that the validation set has data that doesn't have quite as much noise in it. Maybe there aren't a few bad items that are making your model problematic. And so I wouldn't get too worried about this. It may possibly be that your model is not big enough, and if it were bigger, you'd get these two things to align. But having the validation set under the training set is not something to be particularly worried about. All right, let's try dropout next. And the idea of dropout is not much different from what we did in random forests. In both instances, we're going to try to get models that generalize by throwing training data away. And by throwing some of the data away, we create a lower chance that the model is going to chase noise. So I'm going to show you how a dropout layer works, but basically the idea is every time the network is trained, every time it runs through a training session, the dropout layer sets some fraction, which I'll call phi, of its inputs to 0. And then it multiplies the non-zeroed inputs by this fraction, which is, so if phi is 0.5, then it's going to double the non-dropped input. Here's an example. I'm going to have, on average, 1/3 of the values drop out. What are the values it's going to work on? I'm going to have 10 instances where the data is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, etc. I do need to set this option to train, otherwise the dropout layer doesn't actually do anything, but if it's training, it is going to actually drop out. So I execute this, and here's what happens. Look, here, one of the things goes to 0, one of the things, 3 of the things, 1 of the things. So on average, one or like a third of the values are going to 0. And what's happening to the remaining values? Well, if I do this division, 1 divided by 1 minus 1/3 is 3/2. And so the 1, if it sticks around, is going to turn into a 1.5. The 2, if it sticks around, is going to turn into a 3, etc. And so this is what a dropout layer does. Experts are currently recommending riffling a dropout layer after essentially every nonlinearity that follows a linear layer. So you have linear layer, nonlinearity, such as a ramp or parametric ramp or some other things that we haven't talked about yet, and then a dropout layer to prevent overfitting. And I'm going to do that here. This time I'm going to make a network that I'm going to use simplified syntax on, so you can see that again. So here we go. Our linear layer of 50, parametric ramp layer, dropout layer. I'm going to let it pick the, or use the default dropout fraction, which I believe is 20%. We're going to have a linear layer of 30, another ramp layer, another dropout layer, and then into the compressor. We're going to have an input with length 13, and our output's a scalar, and here's a picture of our graph, of our chain, our net chain. Okay, so it just goes straight through. Now, let's train it, and I'm going to use the same stopping criteria as before. The only thing that's different is, remember, when you use the simplified syntax, the data wants to be in the form of all the features, which is going to be a, I think, 338 by 13 matrix, and then all the targets, which is a length 338 vector. So, here we go. you can see, by the way, that our validation set is operating. We're having lower losses on our validation set. Still doing well. And it stopped because evidently there wasn't much progress being made on the validation set. So let's see how we performed. We certainly don't have any overfitting here. The blue line has persisted in being below the orange line. And it's not so good. This is not as good as it was before. Why is that? And the answer is that when you use dropout layers, you have to have a little more patience than I do here, which is what I was using when I didn't have a dropout layer. So what I now want to do is give it 2,000 rounds to mess around. Now there is some risk that if you give it 2,000 rounds to mess around, that you will see overfitting. But sometimes neural networks take a while to kind of find the answer. They kind of bounce around and bounce around. So let's just see what happens if I do the same training operation, and the only difference is I'm much more patient, which is difficult. Right? You can see our loss and what's going on with our R squared. You can see we're not making much progress. Now we are. R squared just went up. You can see for a while it was actually negative, and then the network was really struggling, but it finally has found its way. It's continuing on. Still up, making good progress. Still making progress. Who knows how long we could be here? Looks like it's kind of flattening out. Might have done about what it can. We do have a little bit of overfitting going on, by the way, but see how the orange line is converging on the blue line? We love that. And we're done. Okay, so let's actually see what our performance looks like. And our R squared has improved. It's still not as good as when I avoided dropout, but I'm going to bet that this net is a little more robust in dealing with other data than the network without any dropout. So that's dropout layers. Let's talk about another technique called regularization, which we've seen before, just not in the neural network context. You know, we've actually looked at regularization before. We did it when we were studying forms of regression such as lasso and ridge regression. And if you remember, what we did there was to basically punish the model for having large regression coefficients. And we found that the model actually generalized better often to new data than it did when we didn't punish large coefficients. Now, right now, you can't quite do the same thing in Wolfram language, or I don't think you can, but there is a method that's available that is similar to ridge regression. And the idea is that each time the network goes through training a batch of values, it reduces the weights by just a little bit. And what this reduction does is it forces the network to search for smaller coefficients that tend to fit pretty well. Now, to actually implement this form of regularization, we're going to use an option to net train that we haven't seen before. It's a method option. Why method? Because it turns out there's a lot of ways of doing training. We have not even touched that yet. But one of the things that a net training process has to do is to figure out how to adjust the parameters during the training process. And right now we've been using Wolfram's default method, which is called ADAM, which is short for Adaptive Moment Estimation, which was first presented in 2015, and it's still one of the very strong methods for conducting neural network optimization. You don't need to know what ADAM does in this course, really, But what you do need to know is that you can use atom and force regularization of weights. So to see regularization, what I'm going to do is I'm going to take half of our data. You see here what I've done is to sample half of the 338 positions in the training data. What I'm going to do is then run our net train. I do have some custom settings here. I'm using a very slow learning rate, which you don't need to really understand right now, except to say that it's going to prevent some instabilities that can occur when you have small amounts of data, as I will. And I'm going to let it run and be pretty patient here in the sense that if it can even make this much progress in the R squared within 100 rounds, it keeps going. Right? So let's actually and then what I'm going to do, just so you see, is I'm going to do exactly the same thing. The only difference is that I'm going to have L2 regularization of 0.5. That's a very aggressive form of regularization, but as it happens, it should work decently here. All right, let's pick our random numbers. And now what I'm going to do is I'm going to run these two net train sessions. I'm not going to make you watch them because they take a little while, and we'll come back in a moment. So here we go. All right, I'm going to cut out until those are done. Okay, we're done. And I should caution you, there's some random factors in the training, so your results may vary, as have mine while I experimented with this. But what you can see here is that without regularization, we do have a little bit of overfitting. With regularization, we also have some overfitting, actually. Let's see if the regularization actually accomplished anything. And I guess I'd pre-run this code just to check. It did reduce the sum of the squared weights of the first layer. That's what I'm getting here. I'm using net extract to get the weights out, normaling it so that it's not a numeric array, flattening it, and then taking the sum of the squared using our power total function. I've done that for both the unregularized network here and the regularized network here. And now let's see what the R squareds look like. And the R squared is actually higher on the regularized coefficients, the regularized model, than it is on the original. As I say, it's a very delicate thing here. Sometimes regularization does better, sometimes it's about the same, and sometimes, frankly, when I've run the regularized models, it does worse. But at least you can see an example here where regularization succeeded. We're next going to look at actually changing the structure of the network as a way of reducing the overfitting problem. One of the reasons that neural networks can overfit is that by adding layers and adding nodes to each layers, you're starting to create that universal function approximator, which is great at fitting data, but great also at chasing noise. So by actually reducing the number of layers or making the nodes in each layer smaller, you can often prevent overfitting. Plus, by doing so, you have a network that can train faster, it will use less memory during training, and it will execute in less memory, which can be important if you're trying, for example, to run your network on a small little device, maybe a phone or something even smaller in terms of computing power than a phone. So what I want to do here is to play around with changing the number of linear layers as well as the associated nonlinearities and the number of nodes in each layer and see if we can see whether there's any relationship between the architecture of the neural network and its ability to generalize. What we're going to do is I'm going to make a little function. This is like a total Wolframy thing where I write a function that's going to create neural networks. So here's my function called parametric Boston net. It's going to take a list of integers as its arguments, and it wants a nonlinearity by default. That's going to be a parametric ramp layer. And then it's going to construct as many of these motifs where you have linear layer followed by the nonlinearity as are contained, like if it says 10, 4, 3, that means it wants 3, or I should use 10, 4, 7, it wants 3 layers. The first will have 10 nodes, the second will have 4 nodes, and the third will have 7 nodes. And then at the end it is going to add a compressor, and then we're going to turn that into a net chain which takes 13 inputs and outputs a scalar. So we're creating a function that's going to build neural networks. And for example, here what I'm going to do is just show you how this function works by applying parametric Boston net to these 3 possibilities. Here's one with 2 layers, here's one with 3 layers, here's one with 1 layer, and to produce pictures of the results. Okay, so that just shows you the idea of parametric Boston net. The idea is to make the architecture of the neural network a function of a list of integers denoting the size and number of layers. So we're going to do a big experiment here. I am going to create 250 neural network architectures. I'll train them on the training data, I'll test them on the test data, and we'll see how they perform on the test data. The only little thing I have to do is I'm going to start with more than 250, but then remove what I call bottleneck neural networks, where there's a layer in the middle that has fewer nodes than those surrounding it. Like you have 50 in the first layer, 10 in the second layer, and 60 in the third layer. The 10 is surrounded by things that are bigger than it. And while bottleneck architectures turn out actually to be the key to understanding something called autoencoders, which we will look at towards the end of this course, they're really not good for prediction, so I'm not even going to deal with them. So I'm going to write a little function here that's going to get rid of instances where the middle thing B is less than the thing to its left A, and it is less than the thing to its right C. I'll seed our good old random number generator, and now we're going to create 500 architectures. We'll delete the bottlenecks, and then I'll just take up to 250 of them. All right, and there we go. I got 250. And so you can see here's one where the first layer is going to be 27, the second layer is going to be 32, and the third layer is going to be 72. Here's one that's just a single layer of 72, and we go all the way up to this last one here, which has 8 in its first layer, 99 in its second layer, and 12 in its third layer. All right, so now all I have to do is write a little custom training function that takes an architecture, the training data, the test data, and what I want to measure, and whatever options to net train that I want, and it's going to output a list. The first element of the list is just going to spit back the architecture so we know what we were doing. And then it's going to train the constructed network on the training data using whatever options I specified, and then measure how well our trained network did on the test data with the measurements that I specify. So that's the idea of train with measurements. Now I'm going to write an even more specialized function that says, hey, we don't need it to be general. We want to use the Boston training features and the Boston training targets as our data, and the Boston test features and the Boston test targets as our test material. And here's the options that I'm going to use, that's our function. So now all I have to do is map the train on Boston function onto all of the architectures that we built up here. And so what we should get is a list in which the first element is the architecture and the second element is the R-squared statistic. So I could run this right now, but I actually ran it before. This does take about an hour to run because you're doing a lot of training, a lot of architectures. What I did was I exported it to a file, and then I have a little code here that says, look, if you're in a session and the list of symbols you've defined doesn't include architecture table, that's what free Q means, then just read it back in from the file that you wrote out. And it's this latter thing that I'm actually going to do here rather than break continuity and run this whole thing. So there we go. This is, you'll see, our first neural network with the 273272 architecture got an R squared of 0.709. The second one got one of 0.705, etc. for a number of occasions. And I guess really I should have done the old augmented terse on this. So let's do that. RFI augmented terse. Come on. And I don't know, 5 lines should be adequate for this. And right now it didn't run because now it knew what architecture table was. It was a defined symbol. But trust me, it's in there. And so one of the first things we might want to do, originally I was going to be less ambitious. Let's correct that. Originally, let's take our architecture. Last is the actual performance, the R squared. Remember, there are 2 values, the architecture and the R squared. And then let's make a histogram of it. And what we see is that the R squared does depend pretty significantly on the histogram. There are some disasters over here, but there are actually a number of values in here that are considerably lower than what you get at the higher end. So this immediately tells us that architecture can play a big difference in the performance of a neural network. So then we figure out what exactly determines success. Maybe it's the number of layers. So let's do this. Let's get the first part of each architecture table. That's the 37, 23, 58 thing. Let's take its length. So in that little oral example I gave, it would be 3. So let's group by the number of layers. Then let's snatch the R squared and compute their mean. And we'll just sort this by the number of layers. And what we see is that just having 1 layer on average isn't as good. 2 and 3, basically the same. So maybe by the time we're getting to 3 layers, we're starting to get to overfitting land. Tried a few other things to see if that mattered. I want to look at the maximum value. What's the best we can do with each number of layers? And it turns out that there is actually one in here with 3 layers, which had the greatest degree of generalizability when it looked at the test data. Another thing I might want to do is make sure we don't have a disaster. And so I'm going to look at the worst case for each number of layers. And we can see that we did have a disaster when there was only 1 layer in the network. We got an R squared below 0, which is really, really bad. We also saw, though, that sometimes when you use 3 layers, you might get into serious overfitting, and so you get a lower R squared there. I also thought, hey, let's take a look at the high performers and see if we can see any patterns here. We do see, hey, there's one with 93 nodes, 1 layer, did pretty well. There's our king over here, a 58-124 architecture. The other thing I thought of is, let's look at some statistics. Let's look at the number of layers, the mean number of nodes, the maximum number of nodes, the minimum number of nodes, and something I'm going to describe as the shape. And by shape, I mean, are the number of nodes increasing as we go through the network? Are they decreasing as we go through the network? Or is it a hump where it goes up and then it goes down? We know there are no valleys because I prohibited valleys when I set this experiment up. So that's our shape function. And now we're going to use our knowledge of statistics. We're going to run linear model fit. We're going to compute the length, mean, max, min, and shape of all of our architectures, and we'll use that as our regressor. Shape is a categorical variable, so we will remind Mr. Wolfram of that, and we will get a linear model, a fitted model object, and let's get the parameter table and adjusted R squared out of that. So let's look at our p-values. All this is coming back, and what you see is for most of these things the p-value is real high. Even for length, it doesn't meet the 0.05, but I would say the only really thing that seems to matter much here is length, and our coefficient isn't so big. Our model is not very good at all. That's an adjusted R squared of 0.143. So what do we learn? We learn, I think, that architecture definitely matters, but it's hard to know exactly what architecture works best in advance. There's not a lot of basis here for prediction. So if accuracy is important, some experimentation with different architectures, maybe sampling the data, could prove very worthwhile in constructing a high-performing neural network. We've got two more topics before our journey for today is done. The first is multivariate targets. And here everything we've done up to now in machine learning has basically been to predict one number. Predicting the home price, predicting whether something was a Setosa or a Versicolor or a Virginica. That's really the same as predicting 1, 2, or 3, or -1, 0, 1. Titanic died, survived. You can turn those into zeros and ones. We've just been predicting one thing at a time. And partly that's because that's all a lot of these machine learning algorithms can really do. But what if we want to predict more than one thing at a time? Neural networks can do this, and it really isn't very hard. So, supposing I want to predict not just the home price, but the distance to employment centers for each of those old Boston homes. So let's set up our data, and I'm going to basically move the feature of distance to employment centers over to being part of the target. I think you can follow this code on your own. There we go. And now we're going to construct our architecture. It's the same code as before, except that now that first linear node is only going to get 12 inputs because I deleted one of the features. And our compressor isn't going to compress things down to 2 values. It's going to compress things down to 1 value. It's going to compress things down to 2 values. Other than that, the nodes are the same. The edges, the connectors, are exactly the same. I don't have to do a thing. And the only other thing is for the non-layer ports, I do need to tell it, hey, features is no longer a 13 length vector, it's a 12 length vector. Targets is no longer a 1 length vector, it's a 2 length vector. And predictions also is no longer a 1 length vector, it's a 2 length vector. So let's build that. There's our picture, and you can see that we start with 12 and we end out with 2. We can now put our data in the right form, and let's train away for 30 seconds. And to some extent, I don't really care what the results are here. I'm just doing this to show you that neural networks are capable of predicting more than one thing at the same time. And away it goes. Choo choo chug chug. I'll be back in a few seconds. I think it should be just about cooked. Oh, well, there we are. We're at 85%. Almost there. Great. It's done. How do we know how we did? I constructed a little visualization here. I'm not 100% sold this is the best thing I've done. But the idea is that we have these two-dimensional points. We've got a price for a home and its employment distance. And I show you in blue the actual value of those combinations. And I show you in red the predicted value. So short arrows, like this one here, means we did a good job. Long arrows, like this one here, means our model didn't do such a good job. But there you go. You can use neural networks to predict more than one thing at the same time, which is a very useful feature. Let's talk about developing custom loss functions. The beauty of writing your own loss function is you can train a neural network to basically do whatever you want. The network will dutifully try to minimize the loss function, and it'll create parameters in the trainable layers that accomplish that goal. Here I'm not going to do anything too crazy. I'm going to try to make my loss measure the worst case absolute value of the distances between the targeted value and my predicted value, so that even if a batch gets it really well for a bunch of them, but it gets one wrong, that one wrong is going to spoil everything. So it's going to come up with a fairly conservative method of predicting, and it actually might replicate well. It certainly won't be chasing noise. So how are we going to do this? Well, we're going to need a couple of layers that we haven't seen before. One is a threading layer. And the reason it's called a threading layer is it does very much what Wolfram's thread does. If I take thread and I have some function, let's say the absolute value of the first argument minus the second argument, and I then want to thread that over, here are my first arguments, I'll make it 3, 4, 5, and here are my second arguments, 6, -2, 6. If I evaluate this, it's going to say, okay, 3 minus 6 is -3, but the absolute value of that is 3. And 4 minus -2 is 6, and the absolute value of 6 is 6. And 5 minus 6 is -1, but the absolute value of that is 1. Okay, so what thread does is it takes a bunch of inputs and it applies them pairwise. So threading layer has essentially the same syntax, and this is the same function as I just wrote before. The only thing is, instead of having numbered arguments, I'm going to have labeled arguments. So here's our threading layer, and here's the kind of data that it might like to operate on, where here's our guess, here's our target, and the answer is exactly the same as before. So that's threading layer, and whatever you put in here, those are going to be the names of the input ports. So see, input port, guess, and target. If I said this was my guess, then the input port would be my guess. But let's go back to guess. Okay, so we showed how to operate. The next layer I want to show you is called an aggregation layer. And the aggregation layer just takes numbers in a higher dimension and it reduces them down to some lower dimension using some basic function. Often that function is max. I'll take the maximum, and that's what I'm going to show you here. So let's just build an aggregation layer that takes the maximum of one-dimensional inputs. And now let's take that data that we used up here and we'll run it through a composed set of layers. The first is we'll do the absolute loss, and then we'll find out the worst case of the absolute loss. And you can see this is what I'm actually going to be using to train the network. So the worst case in my example was 6. Okay, now, not really, can't use compositions directly in the neural network architecture, but what we can do is build a little mini net graph. So here's our mini net graph. We have our names of our layers, and here's our connectivity structure. We just take a little pipe from the absolute loss to the worst case. And we'll just double check that this net graph does what we want. Here's a picture of it. Guess and target go into the absolute loss, which in turn goes into the worst case, which produces an output. Just make sure it works, and it does. Okay, so now let's build a network with our custom loss layer. Okay, 50 and 30 nodes for the first and second linear layers. This looks familiar. Everything looks familiar actually until right here, where we have designated, instead of MSE goes to mean squared loss layer, we have worst case loss. That's the name of our worst case loss function layer. Okay, and our connectivity looks the same. The only difference is that the target goes into the target slot of the worst case loss layer slash little mini graph, and also the compressor goes into the guess connector of the worst case loss mini net graph slash layer, and then finally the output from the worst case loss goes to the loss non-layer port. Okay, so let's evaluate our nodes, let's evaluate our edges, let's build our network. Everything here is the same as it was. There it is. And I'm going to use that nifty comparison plot thing where you can see the network training in action. And I believe we are ready to train. We're going to take that new network we constructed with the worst case loss measure. Here's our training data. I want everything, of course. I need to designate our loss function because now it's not sure what loss function to use. If it sees a mean squared error loss, it figures, oh, that must be what you mean. But now I have to tell it, and I'm going to tell it, look, I want you to train on the output from the worst case, which is going to loss. I would like this comparison plot to be visual as we do the training every 1/10 of a second, and I'll let this thing run for 30 seconds. Okay, so here we go. Watch the beginning very carefully. That's usually where all the excitement is. And you can see how fast it converged? And it's converging some more. Those points are always been tricky throughout this whole exercise. They're moving a little bit, but we're having trouble moving them much more. It's just not finding anything that seems to always work on those high value homes. Maybe they had good decorating. All right, and now let's actually make our comparison plot. And you can see that is a respectable comparison plot, really. I should add my usual thing. Let's add an infinite line that runs from 0, 0 to 1, runs through those points, close that up, and there you go. So, respectable training done with a custom loss function. All right, so we learned that neural networks are universal function approximators, which is fantastic. But the fact that they have no bias means that they're very vulnerable to overfitting, or that they can have no bias. So I tried to show how prediction works using simple neural networks, and we ended up exploring 4, didn't we? 4 methods of controlling overfitting. You tell me what I forgot to put in here, and I think what I forgot to put in here is regularization, because actually I added that late in my planning process. And I showed you how a neural network can predict multiple things at once, and we learned how you can make your own loss function and basically train your neural network like a border collie to do whatever you want. Thanks, and next lecture we'll be looking at neural networks for classification. Let's add regularization to the keywords. Okay, that was really